Yes, this topic has been already widely introduced by Enrico Tubaldi in his former comprehensive presentation. So I actually have to acknowledge his contribution to this research activity, which I'm going to present. And I can also skip some slides because we already know what scour is and how insidious it can be for bridge safety, in particular for masonry arch bridges, which prove to be particularly sensitive and vulnerable to this phenomenon because of their age, their high stiffness, and their usually shallow footings. Okay, what is the point? To date, a proper risk assessment procedure is not available for flood events. Unlike seismic hazard, for which we have well-established probabilistic frameworks like the PBE, probabilistic-based engineering, earthquake engineering framework, which is widely adopted even by practitioners. Well, this is not the case when we talk about floods, and so there is much work to be done. And even because a risk assessment procedure will be beneficial for a proper decision-making process. To date, most of the safety management systems base the decision, for instance, to close or not a bridge after a flood simply based on the level of water reached at the bridge cross-section and compared to a, let's say, an event with a 200 return period, for instance, which can be from the safety side or not. Physically, reason behind this choice is lacking. So what we are doing here is, for now, we are working on this part of the framework, trying to provide a better understanding of the response of masonry arch bridges under scour. We try to identify some response parameters sensitive to scour and also easily monitorable, which can be used, for instance, within probabilistic framework for constructing, for the definition of fragility functions at a later stage, and but also can be used to guide the choice of proper monitoring strategies. And so we approach this problem in a numerical way, and also trying to characterize the most recurrent damage mechanisms and scenarios characterizing this type of breach. So we selected a case study representative of a wide set of bridges, let's say of the same typology. Actually, we can see that there are quite common features, in particular geometrical features, among bridges in different countries, in particular in Europe. So we selected ones which is quite representative of this typology. We developed a model, a numerical model, which is developed in Apagus, and it's a continuous solid element model. In which we consider also, beside the nonlinear mechanical and geometrical nonlinearities, we also consider the nonlinearities and the possibility of a separation between critical parts. For instance, we provided some interface elements between spandrel wall and backfill, between spandrel wall and arches and so on. So where we expect some separation, some nonlinear behavior, we modeled these interfaces. Concerning the soil foundation interaction, we adopted a simple Winkler modeling approach, as the one already presented by Enrico. So basically, we use springs, elastic springs, compressive only springs around the footings, and we simulated the progression of the scour by gradually removing the spring, assuming, of course, a scoural shape. This shape is an inverted pyramid with the vertex corresponding to the upstream phase of the pier. This assumption is supported by literature, in particular some experimental results. And so that's the way we simulated the progression of the scour. Concerning the scour parameters used to monitoring the process, there are two alternative metrics. One is the scour depth normalized by the height of the foundation. The other is the scour width underneath the foundation normalized by the total width of the foundation. The latter is better because actually the response of these bridges is quite negligible as long as the scour depth is lower or equal to the height of the foundation. So let's say the system starts to respond only when we start excavating underneath the foundation. And so with the aim of analyzing the failure mechanisms and also identifying some damage states, we analyzed two different scour scenarios. One is local, so where just one pier is assumed to be experiencing this phenomenon. The other is, let's say, more ideal, and we call it global. It would represent a combination actually of different sources of scour, not only local scour, and correspond to a simultaneous developing of the scour underneath both piers. So starting from the local, if we analyze the response, here the response is shown in terms of the response quantity reported here is the vertical sediment of the basement at the upstream phase. So it is reported as a function of the scour in terms of the parameters I said before. On the right, we can see some damage state developing on the bridge. In particular, when the scour is interesting around the 30% of the foundation, we start observing some plastic strain development on spandrel walls. This represents the first mechanism involved, and it represents the beginning of a kinematic mechanism of the bridge. Moving on with the scour, when we are around 50% of excavation, we also observe some pseudo-vertical crack development on piers and in the foundation. And at a later stage, when we are around 60% of excavation, we attain this near collapse condition where typical diagonal cracks develop on arches. And this represents a near collapse condition, after which you can see here the response suddenly rise for very, very small increments of the scour. And similar reasoning can be made analyzing the global scenario. The mechanisms are similar, not equal, of course, but the important thing to observe is that the whole response actually is shifted on the left, meaning that actually lower levels of scour are needed if we have a global scenario in order to activate these mechanisms. And so comparing these results from local and global scenarios, we can observe that actually this 30% excavation underneath the pier represent the level of scour which triggered the first mechanism actually. Higher level of scour are required to lead the system to the collapse from 50 to 60%. This seems quite high value. Okay, it might be surprising to see such high values of scour, but actually this is also observed in reality, where if we look at the post-failure condition of some really collapsed bridge, we often observe a really high level of excavation underneath the pier. So this is a witness of the robustness of the system, let's say. And the other important aspect of this research, as I said, was to identify proper response parameters. and the suitability of this parameter is analyzed by assessing how sensitive they are to the scour, so how fast they grow with the evolution of the scour, and also observing if they have a monotonic trend, because we are not interested in a response parameter showing non-monotonic trend like this. So, for instance, among the sensitive parameters, some which are easily monitorable, can be used even in long-term monitoring, for instance, are the transverse displacement at the top pier level, or even the diagonal relative strains at the diagonal, at the deck level, or of course rotations. These are sensitive parameters. The rotation monitored at the upstream phase of the pier or at the spandrel levels, and so all this information which can be used in a probabilistic framework as EDPs, let's say engineering demand parameters, can also guide the definition of optimal sensor placement. That's just a scheme, but we can, where it is reported some suggestion of possible quantities to be monitored, and also possible tools and instruments to be used for doing that. For instance, diagonal. For instance, even a simple total station can be used to monitor displacement, or why not satellite-based differential interferometry. Okay, that's just a list. And tilt meters. We already seen that actually this is already used for monitoring this issue. Why not vision-based monitoring strategy should be investigated actually. So using low-cost, high-resolution cameras in order to reconstruct the displacement time history at different structural points can be, as I say, the low-cost strategy. We have to check if we have the resolution for doing that. Accelerometers, they are of course useful, even though there are some critical aspects already highlighted by Enrico. When we talk about vibration-based monitoring, what we observe is that actually the frequency variation due to scour evolution are actually negligible as long as the scour is lower than the age of the foundation. So it means that when we start appreciating some variation, actually it may be late, even because we are around here, numerically, we are around 55–30% of excavation. So it's the first damage state identified. So something might be already happening on the spandrel walls, for instance. So on the other hand, we have some higher sensitivity in terms of mode shapes, meaning that even before the total excavation of the age of the foundation, we start observing some significant modification on the transverse mode. Now, this is the result of a numerical investigation. Of course, reality is quite different. There is noise, there is other problems to be considered, of course, but there is the possibility to use this strategy. In conclusion, there are several open issues on this topic, so we are working on it, and of course we have to extend our analysis to a wider set of case studies in order to validate these results. We can also consider different scour scenarios, different angle of attack of the flow, and why not? It would be useful to have a probabilistic hazard discharge model in order to be used in a risk assessment procedure, a model which is able also to consider the refill process after flood events. So there are different aspects on which we should work. It's an ongoing activity, and that's it. Thanks for your attention.